our next machine learning algorithm, that is linear regression. It is a supervised learning algorithm, and it mainly works for continuous type of target data. So as I told you earlier, that supervised learning can be divided in two types. They are regression and classification. So when we have different categorical data as output, then we can go for classification, and when we have some continuous type of target data, then we go for regression. And linear regression is one of the simplest and most commonly used supervised learning algorithm. So we'll go in detail. So what is linear regression? So here we have some features given. It can be one or it can be many, and based on those features we are going to predict the value of one target variable or the dependent variable. Okay, so if there is only one feature and based on that we have to predict the target, then it is called univariate linear regression or simple linear regression. And if there are multiple features are available, and based on those multiple features we have to find the target value, we have to predict the target value, then it is called multiple linear regression. Okay, and actually we when we have the data, the different features, then first we plot them and we try to find some linear relationship between them, and then only we can predict the target value. So by linear relationship we mean that when the independent variable is increasing, then the dependent variable is also increasing, and when the independent variable is decreasing, then the dependent variable is also decreasing. So if this type of relationship exists between the independent and dependent variables, then we can tell that okay, there is a relationship which is a linear, that is existing between these two types of variables. So when we do that and we predict the outcome based on that, then we call this algorithm as linear regression. So we'll go in detail of that algorithm and we'll see that how it works. Okay, so here you can see one simple diagram. So here we have this x-axis and y-axis values. So just consider that it is a simple linear regression, means one feature is given, and based on this one feature I am going to predict the target. So what we have done, that we have just drawn one scatter plot for this x versus y, means x is my independent variable and y is my target or dependent variable. So I have just plotted this. So these are the scatter plot, and there is a red line you can see. So this line is something which is like a kind of close to this all these points. So this is this nature of this relationship between x and y are not they are not falling on a line, but we have drawn some line and we are trying to say that they are the predicted output. So from the diagram itself you can understand that the actual output and the predicted output are not same for all the points. So for these few points you can say for these points it will match, but suppose for this particular input, so for this input value the output may be something 12, but if I go for this line then it is something different, right? So here it can be something 9. So here there is a difference between the actual output and the predicted output. So how it works and how we minimize this distance, that we will discuss in detail. But the purpose of linear regression is that when we have these x and y values, and then we try to plot one straight line and we try to predict the output value based on this straight line. Okay, so the representation means how do we represent the predicted outcome in linear regression. It's very simple. So if suppose x is the vector having some n components x0 to xn, and when I have to predict some outcome based on all these features, then the equation, I can write the equation in this way, that y equal to b plus m0 x0 plus m1 x1 and so on. So this y is the predicted output, and b is called the bias or intercept. So we can keep b as 0, or we can have some value for b, and then m0 to mn, these are called the model parameters or coefficients or slope, and x0 to xn are the feature values. So it's kind of like when we are calculating, so if for simplicity, if you think that there is only one feature x0, then the calculation will be, the equation will be the simplest one, that is y equal to b plus m0 into x0. So if you go to the diagram, so suppose if this is the line, so here it starts from this point, something like that. So it depends on the bias, like that, where from this line starts, and this m value will like whether it will not be equal to x something, suppose x is 5 and m equal to 2, so y will be 10. So it is like every time x will be multiplied by 2, and then the y value will be calculated and the bias will be added. So these terms you should be familiar with. So y is the predicted output, b is the bias or intercept, and these m values are called model parameters, coefficients or slope. Any term we can term them, and x0 to xn are the feature values. Okay, so now as we will go back to the diagram again, so here also you can see that if we assume that for a particular value of x, the outcome falls on this red line, then for the particular set of x and y values, I can see that there is some difference, means the predicted value is not matching with the actual outcome. For some of the cases it may match, for some of the cases the distance may be very less, but for some of the cases I can find that this line has some difference with the actual points. Okay, so this also we need to calculate. So this when we calculate this, that is called cost function. So before going to cost function, we'll see this diagram. So suppose these violet points, they are the actual outputs for a particular value of a feature. So if you consider that feature is plotted in the x-axis and the outcome is plotted in the y-axis, then what is this violet point? It is for a particular value of feature, what is the particular value of the outcome. So if violet one is the outcome and this blue line, this is the predicted value line. So I am assuming that when for this particular value of x, this point is the predicted outcome, and this violet one is the actual outcome. So this is the distance between this predicted outcome and actual outcome. So for this case also, this is the actual outcome, and the predicted outcome will always fall on this straight line. And for this point also, it is in the negative side, but also there is a difference. So these violet points are the actual outcome, these blue line points are the predicted outcomes, and this difference is called the residual. Okay, so now we'll have some equation for calculating this cost function. So what is the cost function? It is the total, you can say, the distance between the actual points and the predicted points, and total difference, and it mainly helps us to predict the values of intercept and coefficient. Okay, the purpose is that why do we calculate cost function? Because it is important that we should predict the values which is very close to the actual value, because if our prediction is something which is very far from the actual value, then the purpose of the algorithm does not serve. So when it will be the very good algorithm, when it is predicting the correct outcome as much as possible. So here our purpose is to minimize the error between the predicted value and actual value. So you understand that in this diagram, if these distances are very less, then I can say that okay, I can predict very close outcomes, and if there are a lot of distances between the predicted value and actual value, then it will be very difficult. Okay, so how do we calculate this cost function? This is also called mean square error function. So this function is something like, you can see this this notation j is termed as the cost function. It is 1 by n. 1 by n, this n is nothing but the number of features available. So it's like, what I am doing for each value of n, what I am doing, this spread is the predicted output and y is the actual output. So I am getting the difference between this predicted outcome and actual outcome and doing the square of that. So y square, so this distance, you understand, right? So suppose for this particular diagram, suppose I have 4 values of x and 4 values of y. So what is the distance? It's like this one and this one and this one and this one. So all these 4 values, I can take the calculation and I can say that, okay, this is the total difference between the predicted value and actual value. But here the problem is that here if I calculate the distance, so it will be in the positive side and this distance is in the negative side. Maybe the outcome will come as a negative value. So if I just summarize this, means I do the summation of all these 4 points, then what will happen, that it will just deduct something. So maybe this length is 4, this length is 4 8, and then if it is minus 4, then it is actually 4 plus 4 minus 4. So it will come as 4, which is not correct. I have to calculate the entire distance. So that's why we take the square of that. Okay, so for n number of value points, I can say that this is the total cost. Okay, so our purpose is that we cannot change x, so that is fixed. So in our equation, when we are calculating y, you understand that what I can change b and m. X is fixed, I know the value of x, based on that I have to predict y. So if I can change b and m in such a way that the total quantity of error is minimized, so that is the purpose that I should do while I am doing the linear regression. Okay, so that is the cost function and our purpose is to minimize the error. Okay, so when there is only one input, means only one, based on one feature I am doing the outcome calculation, so for that we use this ordinary least square method or Weyl method. So what is the main objective is, of course, to minimize the cost function. It is useful for univariate linear regression, and this is the formula that is derived. We are not going in the much mathematical details, but this is the formula, that when I have 1x and 1y, means 1x means only one feature, the one independent variable and one dependent variable, then we can calculate m and b in this way. So here x, you understand that xi is all the x values, means different values of x, and x bar is the average, the mean of all the x values. So here I am doing the difference between xi and the mean of x and multiplying with yi minus y bar, which is the again the mean of the y values, and then I am dividing it with xi minus x bar whole square. So that value when we calculate, then that gives the optimal value for m, and similarly b is y bar minus m into x bar. So this is the formula for ordinary least square method. So this formula can be used to minimize the error in the univariate linear regression. Okay, now it is another algorithm. This is called gradient descent algorithm. So this is again, the purpose is to minimize the cost function. But it is mainly useful for multiple linear regression. Actually, the formula we have used, that is okay for single value of x, but when there are many x, that means we have x1, x2, x3, x4, like many features, then we cannot use this method. So in that case, we'll go for this gradient descent algorithm. So here how the process is done, I will go to the diagram first. Okay, so suppose it's kind of this type of structure. Okay, suppose I am here. So this point, this is called the minima. This is the global minima. Means if you can compare with a kind of mountain, so if these are the two peak points suppose, and this is the lowest region of the mountain. So my purpose is that I have to reach here. So wherever I may be in this entire curve, but my purpose is to reach here. So this is the point where your cost function will be the least one, means you are very close to your actual outcome value. Okay, so here we have to reach, and how we are going to reach? So I can be anywhere in this curve. So suppose I am here, so how I know that I have to reach the global minima? So what I am doing means, actually how this algorithm works, so it just changes small values, means very small changes in the values of m and b, then it calculates that where it reaches. So this way, by changing the value, small value changes, I can reach here. Okay, so once I reach here, suppose I again make some changes to the values, and then I reach there. So I understand from the outcome that okay, I am not in the minima, I already left the minima. So this way, if I do it for some more iterations, I will understand that this point is the maximum one where I had the least error. Okay, so this way I can move and I can go to the global minima. So there is a term called learning rate. So what is that? Learning rate is like how you are changing the values of m and b. Okay, so here what we do is start with random initialization. So random initialization means we give some value to the bias and the coefficient. Okay, so the intercept and slope, whatever term you say. So I give some values to them, and then we change the values iteratively to reduce the cost. So there is a very small change is done, and then again the cost is cost is calculated. So this way, again and again we change the values, and we see that what is the cost now, what is the cost now. So this learning rate is number of steps taken. Okay, so means how I will go, means in which rate I will change the values for my slope and my bias, right? So the problem is that there are two types, means I can go with very small learning rates, means I can change them very slowly, the values of this bias and this slope. So the problem is that there is a chance that we will reach to the minima, but it will take a lot of time. And if we go with larger running rate, then it reaches fast, but the problem is that it can overshoot the minima. What does that mean? So if you go to the diagram again, so suppose this case, it is a big learning rate, means I am making the changes, big changes at a time. Okay, so here suppose I was here at this point, so I make change to this bias and slope in such a way that instead of going here, it directly reaches this point. So you understand, I was here, but I could not move here, instead I went there in some other point, and then after change I again came here, after change I again came here. So this way I am moving very fast, but maybe it is this minima I can never reach. So that is the problem with big learning rate. And for small learning rate, what may happen, that I am here, so I am making some small changes, so I am going just like that. Okay, so there is a high chance that I will reach the minima always. But the problem is that suppose I was here and I am making very small changes, so I will reach there, but it will take a lot of time. So this is the concept of learning rate. And actually these algorithms, sklearn library already contains the algorithms, and mostly it is handled well, but we have to understand the concept, so that when we really write those algorithms on our own, then we should take care of these things. So what is the difference between small learning rate and big learning rate, and what is their impact? It's very important that we understand. Okay, so there are three types of gradient descent algorithm. They are batch gradient descent, stochastic gradient descent, and mini batch gradient descent. So batch gradient descent is here all training examples summed up at each step to calculate the gradient of the cost function. Okay, so here what we do, that we take all the training examples, the entire set of training data is taken, then it is summed up, and then only the gradient of the cost function is calculated, means what will be the next value set of this m and b, that is calculated based on the entire training data set. So you can understand that when it is a huge data set, then it is not a good idea to implement this. Then comes stochastic gradient descent. So in this type of algorithm, one training example is selected at each step. So at a time only one training example is taken, and based on that the m and b values are calculated, and there is a random shuffling, means in one iteration suppose one training example is taken, and the next iteration another training example is taken. This way it calculates the gradient of the cost function, and as only one training example is taken, so it is suitable for very large data set as well. And it is actually used for larger data sets, and computationally also it is faster. So it's a commonly used gradient descent algorithm. There is another gradient descent algorithm, that is the mini batch. So it's kind of existing in between batch and stochastic. So in batch the entire training data set is taken for calculation, and in stochastic gradient descent only one training example at a time is taken. But in mini batch gradient descent, instead of one there are n samples are taken, means n is a value which is changeable, means if you take n equal to 1, then it becomes stochastic. If you take n equal to the entire data set, it becomes batch, and in between you can take, so that you can handle a large data set, and you can handle it to calculate the cost in a more effective way. So you can change the value of n based on the type of your data set, or the nature of data, or the processing speed requirement, all this. So it comes between this batch and stochastic. So these are the types of gradient descent algorithms. So we have covered what is linear regression, and then how the cost function is calculated, and how do we handle actually the minimization of cost function in different ways for single linear regression and multiple linear regression. In the next phase of sessions, we will do some hands-on on linear regression, so that will be more clear that how it actually works. Okay, so thank you for now.